Hello, hello everyone. Good morning, good afternoon, good evening, depending on where you all are. I'm Aditya, and I hope everyone can hear me. Uh, I I will be your host for today. So, without any delays, let's start the session. So, the speaker for today's session is Mr. Roozbeh, and he will be presenting a session on webinar on power quality studies with DIgSILENT PowerFactory. So, a few words about the speaker. So, Mr. Roozbeh is a PhD candidate at the Department of Electrical Engineering in Eindhoven University of Technology in Netherlands from 2019. He is also a PhD researcher at Tenet TSO, the transmission system operator of Netherlands. He was previously with Esfahan Regional Electric Company, an Iranian TSO, as power system planning engineer, and he collaborated with Universidad Loyola Andalusia in Spain, working on Flexi Transtor and EUH 2020 project. Mr. Mr. Torkzadeh major interests include smart grids, synchrophasor technologies, and power quality. He has been involved in numerous industrial and research projects related to power system planning, operation, and controls. Thanks to these experiences, he has authored and co-authored several conference papers organized by well-known institutions like IEEE, CIGRE, six journal papers published by eminent publishers including Elsevier and IET, and three book chapters published by Springer. Torkzadeh is a graduate student member of IEEE Benelux section and member of Next Generation Network, CIGRE Netherlands. He's been recently awarded by CIGRE C4 Study Committee as the winner of NGN Showcase presentation on a virtual Centennial session of 2021. I hope everyone will find this session useful. And with this, I'll turn over to Roozbeh.
Thank you, Aditya, for the introduction. Hello, everyone. Good morning, good afternoon, and good evening. This is Roozbeh Torkzadeh here from Netherlands. And today we'll discuss about how to do power quality studies in DIgSILENT PowerFactory software, which is a power system simulation platform. And I ask for your apologies because actually I had a cold last week and I've not fully recovered yet. So maybe we'll have some coughing during the talk. In this presentation, I'm going to talk about the power quality phenomena in a nutshell, and then I will discuss two major phenomena in detail, which are the voltage dips and harmonics in power system. For voltage dips, we are going to take a look into how to calculate residual voltages and also how to see the area of propagation of an event. And for harmonics, we are going to first talk about how to model the harmonic sources and also background harmonic in PowerFactory, then how to do a harmonic load flow, and then how to see the distortion plot and also waveform plots. And finally, we will conclude this presentation with how to do a frequency sweep in PowerFactory. And hopefully, we could have a Q&A at the end. As a head up, this workshop needs a basic knowledge of the PowerFactory and is a kind of prerequisite for this workshop. And I really want to appreciate the organizing committee of the Power the Future Summit, also IEEE Power and Energy Society, and the young professionals of IEEE PES. So in the introduction, power quality is actually a very broad concept. Various phenomena can be considered as power quality phenomena, but power quality mainly discusses the quality of the delivered power to the clients. From the waveform perspective, we can distinguish between these phenomena. For example, in this figure here, in this slide here, you can see 5 different waveforms. The first one shows a voltage dip. A voltage dip or a voltage sag happens when the voltage drops to a value lower than 90% of the original value in a certain duration of time. And In the other hand, we have voltage swell, which is a kind of overvoltage, but it's not a steady state overvoltage. It happens during a time and when the voltage raised more than 10% of the original value. Then we have the harmonics. They happened in the grid majorly because of nonlinear loads, because nonlinear load can create some distortions in the current, and consequently the voltage will have those distortions. And then we have the voltage imbalances, flicker, and other phenomena like supraharmonics and etc. And all of them could be considered in the power quality. They could be under the umbrella of the power quality phenomena. But today in this presentation, I'm going to talk more about two phenomena: the voltage dips and harmonics. This is due to the fact that these two are maybe the most important ones because they can have impact on both clients and also the grid and the equipments in the grid and also the equipment in the client side. And because of the energy transition, there will be some changes in the grid, and this may intensify the propagation of voltage dips through the grid and also the harmonics. First topic to discuss is the voltage dips. And maybe the best question is, what is a voltage dip? As it can be seen here in this figure, when the voltage magnitude drops to a value between 1 to 90% of the original value for a certain period of time, for example, in this figure, you can see that for this period of time, we have lower voltage magnitude than the normal one, and this causes a voltage dips in the network. These voltage dips may cause interruptions into the production lines, or they can stop the ventilation systems of animal farms, for example, the pig farms, and this may lead to huge financial losses. So it's good to know why we have them in the grid and how we can prevent them. The origins of the voltage dips are mainly due to short circuit faults in the grid, but also rarely it's happened when some elements are have switched in the grid, but it's not common. Based on the impedance from the location of the event, each bus experiences a certain residual voltage from the voltage dips. Therefore, if a client is located far enough from the event location, it will not experience huge changes in their voltage. So not all voltage dips are harmful. Therefore, according to the depths of the voltage dip and the retained voltage, which are these two over the RMS signal of the voltage, we can distinguish between the voltage dips. Standards provide tables to classify the voltage dips based on their characteristic. For example, here I put a table from EN 5160 standard. In this standard, 4 classes have been introduced, in which class A is a unharmful class, and if a dip happens in that class, the customer can prevent the consequences by spending a reasonable price. So the voltage dips within class A are not important, but for other classes B1, B2, and C, it's important to limit the number of those voltage dips. And this is where grid codes define precise measures that, and also precise limits that for each voltage dip, for each client at each network, there should be a limit. And if that limit exceeds, we need to investigate about the origins. So the first step to understand what are the voltage dips is to do the voltage dip assessment. And this assessment is done by voltage dip simulation and calculation. According to literature, various methods can be used to simulate and calculate voltage dips. Steady-state calculations can reveal the depths of the voltage dip. However, using the phasor domain simulation, we can have RMS values during the event. Therefore, we can simulate both residual voltage and the duration of the voltage dips. And finally, the most detailed simulations are time domain simulation. They can produce the waveform for the voltage dips. Therefore, we can see all the characteristics of the voltage dips. According to the requirements of each study, we need to pick a proper method. In this workshop, I'll investigate the voltage dips in presence and also absence of renewables. Therefore, a steady state calculation would be enough, and especially because we are focusing on the grid level. So steady state would provide us enough information to reveal what will happen in future with renewables. Before switching to PowerFactory to show you how we do this calculation and simulation, it's better to introduce the model. I'm going to use the IEEE 39 bus test case system, which has a 345 kV transmission network. This model exists within the examples of PowerFactory, so you can easily use that model. And now let's switch to the software. So this is the main window of PowerFactory. I already create two projects, one for voltage dips, one for harmonics. First, I'm going to activate this project for voltage dip. Here you can see the test case system, the IEEE 39 bus. And as you can see, you can do different analysis, for example, load flow analysis, short circuit analysis, and then here you have a whole list of different type of analysis that you can do. And today we are going to focus on power quality and harmonic analysis. But before getting to that, I applied some changes to the grid. So I put this unit here as the slack bus. So initially in the model, this G2 is the slack bus, but I put this G1 as the slack. And also I modeled two PV plants here, and I'm going to talk about this later. But to see the voltage dips, I'm going to put a short circuit fault at bus number 16. For doing that, you need to right click on the bus and then go to calculate and then select short circuit. Here in the window, you can see that you can calculate the short circuit based on different methods. I'm going to use this IEC 60909, and also you can select the version of the standard that you want to use. In 2016, they also considered the contribution from the renewables, so I will select this one. It will be a three-phase fault with maximum short circuit current. You can select maximum or minimum. There are some variations in the standard that you can refer and see what are the differences. And also the fault impedance is 0. So when I execute this calculation, you can see that software puts the short circuit here, and then it's going to show you some result in those result boxes. For example, in this result box, you can see that the short circuit power is 9.981 gigavolt ampere, and the short circuit current is about 16 kiloamps. But also you can see the voltage at this bus bar equals to 0 per unit. So which is rational because we had no fault impedance and we expected to see 0 for the voltage at this bus bar. But when we move further away from this bus bar, for example, to bus number 15, there is one line between them, and this line has the length of about 38 kilometers. So there is an impedance between these 2 points, and you can see here that the voltage at this bus bar is 0.17 per unit, not 0. So the further we get from the location of bus, we can see higher values for the voltage dips. We can plot them in a bar plot. So in order to see what is happening for the whole grid, but not just one of them, we can click on this plus sign here, then select a plot page, call them voltage plot, and then execute it, right click, insert a plot, and then from general plots, we are going to select a bar plot. So in this bar plot, I want to plot the retained voltage for all the buses during the event. So it asks me which element I want to select. Here I append, let's say 2 rows. For the first one, I'm going to, within my grid, I'm going to pick bus, let's say bus 16. And then within my grid, let's go for bus 15. Also, let's add another bus, so append a new row. And this time, for example, bus number 2. So these 3 buses, and then for these buses, I want to plot the voltage. And from this short circuit calculation, not from the load flow or anywhere else. From the short circuit calculation, from this current, voltage, and powers, I will pick this U, which is the voltage during the short circuit. And you can see that the voltage differs per node. And the further you get from the fault location, the value of retained voltage would be higher. So I already create this plot for all the buses, and you can see this fault would be would create a severe voltage dip for clients installed at bus 15, but for sure clients at bus 39 wouldn't be impacted because they are close to the nominal range, which is from 90% to 110%. And this is how voltage dips propagate through the grid. So let's switch to the presentation. As you saw, voltage dips can propagate through the grid, but this propagation could be vertical and horizontal. So for example, in this case, if we put a fault here, you see that each node can experience a different retained voltage. And here in this figure, you see the heat map of this propagation through the grid. So the more reddish is the area, it means we have the lower retained voltage. And the more greenish, for example, at this bus 39, it means that we are close to the normal values. Also, voltage dips can propagate vertically through the grid. It means that goes from one voltage level to another voltage level through the transformers. It depends really on the fault type and also the winding connection of the transformer. But actually, according to a study, about 30% of voltage dips that were experienced in the medium voltage grid were due to the faults that has happened in extra high voltage or high voltage network. So this is also a thing to consider, because with this kind of heat map, we can see the horizontal propagation, but also it's important to consider that there would be a vertical propagation too. So I'm going to show you one example with PowerFactory, but before getting to that example, it's good to see it here. So you know that the renewables are going to connect it to grid because of energy transition. So we want to be more sustainable. We want to have a higher share of renewables. And those renewables are majorly interfaced with the grid with inverter. So we call them inverter-based resources, or IBRs. And the problem is that IBRs are not similar to synchronous machines because IBRs have a limited capacity to provide short circuit power. Also, you may hear that they have also a limited capacity to provide inertial response, but that would be a different story. Right now, I'm majorly focused on the short circuit power. So they have a limited capacity to provide short circuit power, and this may lead to have deeper voltage dips and wider area of propagation. Because synchronous generations can provide a support during the voltage dips to keep the voltage within some specific limits. But if we don't have those synchronous machines, the situation would become problematic. In the example, we are going to replace two synchronous machines with IBRs, this G2 and G3. But also I have a figure here to show you what will happen to the grid if we just put these two units out of service. So not replacing them with IBRs, but just putting them out of service. And this is the result I have. So if you put them out of service, the area of propagation would increase, and therefore more clients would experience a severe voltage dip. In this example here, actually, I compensated the active power from these two generations from the slack bus, so the load flow converge. But in the example that we are going to do together in PowerFactory, we will replace these two with two IBRs. And one point is that these figures are created with a different simulation platform, and also I use Python for the illustration of the impact. So we are not going to reproduce exactly the same figure, but somehow same figure with those heat maps. Now let's switch to PowerFactory. So here is our grid, and you can see that I put already two static generation units here. These are representing PV plant. Let me run a load flow here. So you can see that the active power from this unit is about the transit power from this transformer is about 500 megawatts, and the voltage at this node is 0.98. And when I put this one out of service and then switch this renewable plant in service, you can see the same amount of power that is flowing through this transformer, and also the same voltage value here. So practically from the load flow perspective, these two generations are equal, but the point is that this PV plant is not able to provide any short circuit support. So within this short circuit tab, I selected this no short circuit contribution, which is actually the case for some of the power plants, for renewable power plants. Yeah, for newer technologies, it is possible for them to inject some current during the fault. But the point is that value could be around the nominal power. So it's not like the synchronous generation that they can provide you with multiple folds of their nominal current. So we have two options to go with no short circuit contribution or with contribution. I'd rather to start with no short circuit contribution. But before doing so, let's plot the heat map for the base case. And one point, I did the same also here. So we have replaced this G3 with these solar power plant. So when I put everything back in service, let's do a load flow. Okay, everything is fine. All the buses are green. It means that they are within the specified limits. Now I'm going to put a short circuit on bus 16. Again, a three-phase fault according to IEEE 60909. Now for creating a heat map, first we need to define a palette for coloring. For doing that, you need to click on this palette logo here, and then from this third option, you need to go to user define, and then click on this manage filters. So I already created a filter, but for you it would be empty. So you need to define yourself a filter. I'm going to show you how. You need to click here and then select this filter set. And then you can put a name here. So voltage deep coloring. And then within this set, you can append rows. So let's put, for example, 6 rows here. and you need to define a name for each of them. So for the first one, I'm going to put, for example, voltage higher than 90%. And then it asks me for which object. I'm going to apply this filter on my terminals. And in PowerFactory, we know them with this one. So they have the extension of .elm TRM. So it's element terminal. And then we need to add an expression here. This expression could be, This expression could be something like this. So for the voltage value, if it's higher than, I can remove this part. So if the voltage value is higher or equal than 90%, let's show green. And then you can do it for other criteria that you have. So I already created this one. You can see that I have different limits. If the voltage is less than 10%, we will have this very red color. Then if it's lower than 30%, but higher than 10%, we will have this orange color. And by increasing the voltage, we will have more, we will be more close to green. And finally, we have this very green for voltage in the nominal range. So when I select this one, and then click on this logo here, which is heat map, it will ask me some questions. So I would say just leave it as it is and just execute it. And now you can see how the voltage dip has propagated through the grid. It is not exactly like the figures that I've shown on my presentation, but you can see a heat map. So if you are a client and you located within this area, it's highly probable that you face with a very severe voltage dips. If you are in the yellowish area, you would be in some moderated classes. And then if you are in this green area, so you will be safe. And as you can see, we also have these two grayish area here. This is due to the fact that I have two elements which are out of service. So we have no voltage value for them, and the PowerFactory consider gray for them. So in this base case, when we have the synchronous machines in service, you can see that the bus here is greenish, and also we have semi-greenish area here. But let's see what will happen if we replace those synchronous conventional generation with renewables, with PV plants. So I'm going to put this unit out of service, also this unit out of service, and replace them with some renewable units. I'm putting these renewables in service. Now let's calculate the same event. You can do it by clicking here and select calculate, or because you have formally selected the bus, you can use this logo here to calculate short circuit. And when you click it here, you can see that the user selection is bus 16. So I'm going to redo the calculation and now redo the heat map. And as you can see, we have much wider yellowish area. So all the clients and connected parties that are located in this area of the grid would suffer from a moderated or maybe a severe voltage dip. And this is a thing that we need to think about it for the future. So if we are going toward more and more renewables, we need to also think about the short circuit power changes. And maybe the point is not having a lot of renewables, but is about fluctuating between a lot of renewables and sometimes some synchronous machines, because we know that we need to forecast the wind, and also there will be some clouding which impact the solar parks, and these fluctuations in the output power of renewables would lead system operators to put in service some synchronous generation. But these changing from renewable to synchronous and synchronous to renewable will cause higher fluctuations in the short circuit power, which can impact the voltage dips, also can impact the protection system, and we need to think about it. So this was basically the things that I wanted to show about voltage dips. Now we can go to the other topic, harmonics. The main idea of the upcoming slides comes from the graduated course on power quality in Eindhoven University of Technology, and also especially the harmonic sessions, which are presented by Dr. Vladimir Chuk. The distortions in the waveform of the voltage or current are harmonics. And for example, here you can see a pure sine wave. It is undistorted. But when we have the distortion, we will see some waveforms like this. But to understand what is the harmonic content of this waveform, we need Fourier series. The Fourier series transform makes it possible to deconstruct the complex waveform into a series of simple sinusoids, which start the power system fundamental frequency. And by adding up those frequency, we can have this final waveform. So here you can see, for example, if we use the Fourier series transform, we have these signals. So if we add up these three red, yellow, and purple signal together, we will have this blue signal. And in this example, you can see that the distorted waveform is formed by summation of these three pure sine waves. One of them has the fundamental frequency, so the frequency of the red one is equal to the frequency of this blue curve here. But the other one has a threefold and fivefold frequency of the fundamental signal, and we call them third and fifth harmonic. Also, we can look at this phenomenon from the frequency domain perspective. If we use the Fourier transform, we can convert this distorted signal into its frequency components, and you can see the magnitude of each of these harmonics. For example, we had 100% for the fundamental one, about 30% for the third harmonic, and 10% for the fifth harmonic. But why do we have the harmonics in power system? As you may know, and I already mentioned it, harmonics in power system are majorly due to nonlinear loads. For example, the semiconductor devices like transistors, IGBTs, MOSFETs, diodes, also some regular office equipment such as computers, printers, fluorescent lighting, battery chargers, and some equipment within the grid, for example, overflux or saturated motors or saturated transformer can produce harmonics. There are various assessment indices for harmonics. Two of the most important ones are harmonics distortion, or HD, which shows the share of each harmonic in the distorted signal, and the total harmonic distortion, or THD, which shows a cumulative number for all harmonics order in the signal. Also, there are two different methods to calculate THD. One of them is based on the fundamental factor, this one, and the other one is based on the RMS value of the distorted signal. And I will show you that you can have these two values within PowerFactory. Before getting to the PowerFactory and do the simulation, it's good to also introduce the model here. The model is a 10 kV medium grid network with two feeders, and also there is a jumper section here, which can change the radial configuration into a meshed configuration. This model initially developed by Dr. Tony Xiang, also from Eindhoven University of Technology for the graduate course on power quality. And now let's switch to PowerFactory. So for this one, I prepared a different example. So I'm going to activate this model. So We have these two feeders, we have this cable. This cable could be out of service at the beginning. And let me run a load flow. You can do it by pressing F10 on your keyboard or clicking here and then running execute. Before getting to doing the analysis, first we need to introduce the harmonics in the system. So we need to define the harmonics load here. For doing so, we can right-click on a load that we want to define it as a harmonic source, click on Edit Data, then we need to select the type for it. So from here, we are going to create a new type, and it would be a general type load. Let's put it harmonic load type. And then when you define the name, you need to go to this tab, Power Quality Harmonics, and select current source. So the most important factor is to select this current source here. When you select this one, you can go to Power Quality and Harmonics tab in the element. And from this harmonic current, you can create or select a type. So I'm going to create a new type for this one. It would be the harmonic source type. And here you can input the values with regards to your load. And there are different methods. You can enter the values for a balance load. So here, because it's a balance situation, it's going to have only specific harmonics. You can add the value for the magnitude and also for the phase angle. The other solution is to have an unbalanced one, and for the unbalanced load, you can have a different harmonic, even for even harmonics, third harmonic, fifth harmonic. So you add the harmonic order, then for each phase of the system, for phase A, B, C, you can add the harmonic value in percentage for the magnitude and also in degree for the phase. And the other one is according to IEC 61000. And for this one also, you can add the values. So for the second harmonic, third harmonic, and so on. For this example, I'm going to select this balance one and just, let's remove these two. Yeah, let's put 30% here, and 20% for the seventh harmonic, 5% for 11th, and 5% for 13th harmonic. And the value should be in percentage, so they are 30, 25, and 5. And then press OK. Now we will have a load which got some harmonics in our system. To investigate the impacts, we need to run a harmonic load flow. So instead of doing a regular load flow, we need to run a harmonic load flow. For doing that, from this drop-down menu, we need to select Power Quality and Harmonic Analysis. And here we have different analysis type. The first one is Calculate Harmonic Load Flow. In this one, you can go for balanced, unbalanced network. Here we have a balanced harmonic source, so I will select the first one. Then it asks you if you want to calculate for a single frequency or for all frequency. I'd rather to go for all frequencies so we can see what is happening. Then here you can also select for which harmonic you want to see the result in the result boxes here. I mean these boxes here. So for example, I'm going to see the result for the fifth order harmonic. It asks you if you want to calculate flicker or not. And if you're interested in knowing more about it, there is a golden rule in PowerFactory that in each window, if you press F1 on your keyboard, it's going to open a PDF file. And within that PDF file, you can understand what is happening with that. For example, harmonic load flow, what are the different options? So I'm not going to explain all the options to you, but yeah, maybe just this one, for example. Here you can select if you want to calculate the THD, it would be based on the fundamental or the RMS. And the fundamental is more general, so I will keep it as the fundamental. And then I click on execute. Now you can see that for this bus bar, I can see the THD, the total harmonic distortion, and also the HD, which is the harmonic distortion, but for the fifths. If I want to see the value for the seventh order harmonic, we need to click here again, and then put 7 here, or put 350 here. It doesn't matter. You can put either of these two. And then when you run it, you can see that the value has changed to 1.6. But maybe this is not the case because you want to have an overview on what is happening on the grid. So you don't want to see or run this calculation for each harmonic order. You want to see everything together. For doing that, you can plot some bar plots, and from this logo here, create distortion plot. You can select this harmonic distortion and press OK. It will ask you for which elements you want to see the result. Yeah, for example, in this case, I want to see the result for the 10 kV bus bar. And for which variable I want to see the harmonic distortion. And when you press OK, you can see this nice curve here. So let me do this. So you can see that for the first harmonic, we have the magnitude of 100%. And for the other harmonics, it's not that much. So you can, for example, focus here and then press this one. So for the fifth harmonic, the harmonic distortion is about, let me also make it a little bigger. It's 1.6, and for the seventh harmonic, it's 1.5. And also for the 11th and 13th harmonic, you can see the values. So this is one of the objectives of doing power quality analysis with PowerFactory. Also, we can do one thing more with this harmonic load flow. Basically, this load flow is a regular load flow, but for different range of frequencies. So when we have the result for different range of frequency with a Fourier transform, we can convert those frequency values into a time domain signal. And the thing that I want to mention is that with PowerFactory, we can create some waveform signal. In order to do so, we need to define some monitoring variable. For example, I'm going to show you the waveform of the current for this cable. I'm going to right-click on the middle of the cable, then go to this define option, and from here, result for harmonic load flow. For this cable one, I want to see the current, but not only the magnitude, I want to also see the phase angle. So I will select also this one. When I have selected both of them, I will redo the calculation. And now, instead of going for this distribution, harmonic distortion plot, I'm going to select this waveform plot. For cable 1, this is my magnitude, and it's going to fill the angle automatically. And then let's remove the first plot. You can see this is the waveform of the current. So you can see those distortion in the waveform. Also, we can do a check. So if we change the type of list load from a harmonic source into an impedance model 1, we don't have any harmonic source anymore, so we expected to see a pure sine wave here. And let's redo the calculation, and yeah, we have the pure sine wave here. So with PowerFactory, you are also able to see the waveform. However, it's basically a RMS domain or phasor domain simulation tool. Then let me show you something else. maybe sometimes you are not the one who producing the harmonic, but some other clients or connected parties which are connected to the grid somewhere else are producing for you some harmonics. So in order to do so, we can apply the background harmonics. Here I have an external grid which represent the rest of the grid. If you double click on it and go to this power quality harmonics section, you will have this harmonic voltage tab. And as you can see, you can add the value for the magnitude of the harmonic for different order. For example, for the third order, I will put 0.3, and the value here are in per unit, not percent. So for 30%, it would be 0.3, and for fifths, let's put 0.1. And now let's see what is the waveform of this line. So I will do the load flow, the harmonic load flow again, and you can see the distortion again in the current. And this distortion is not due to the fact that you are producing the harmonic, but that someone else, somewhere else in the grid is producing the harmonic, and it can impact you. And the final analysis that I want to show you is, let's switch to the presentation file, is the frequency sweep analysis, and hopefully after that we could have a Q&A session. So frequency sweep analysis is another type of analysis that you can do in PowerFactory. It's basically running the load flow for different frequencies with a time step, or sorry, a frequency step that you design for a specific range of frequencies. With this kind of analysis, you can plot the network impedance frequency characteristic, the figure that we have here, and you can see how the impedance of your grid is changing for various frequency. It is a very important chart for you as a grid operator, and also if you are a connected party, you want to see what is the behavior of impedance at the bus bar that you are going to be connected to. And if there is some resonant frequency, maybe it's good to think of a filter to change the frequency to a higher range, which is not probable. For doing this analysis, let's switch back to the PowerFactory. So for doing this analysis, I'm going to run this option, calculate impedance frequency characteristics, or in short, the frequency sweep. It can be done in balanced and unbalanced mode. I'm going to select the balanced one. It asks you about the starting frequency. I put 50 Hertz here, which is the nominal frequency of the grid, and the stopping frequency, I put 10 kilohertz here, and I put the step size of 0.1 Hertz, which is a little bit too low. We can increase it to 1 Hertz, but because the whole simulation is not going to take a lot of time, so I will keep it 0.1. And then I will execute this simulation. It's done. For plotting the result, you need to create a curve plot. But before doing this analysis, we need to define the output variable or the monitoring variable. So, for example, I'm going to plot the network impedance characteristic for this node. I should right-click on the node, go to Define tab, then go to this one, Result for Frequency Sweep. And then for this bus bar, I'm going to just show the values of the impedance and also the angle of the impedance. So for these two variables, I will run the calculation again with the same settings. And after simulation is done, we click on this logo here, and we can select this one, curve plot. So I'm going to select bus number 1 and the impedance magnitude. So here you can see those peaks Those are the frequency that in which if you provoke the system for those frequency, you will see a high impedance there. Also, I can copy and paste this chart. And for this one, I can select the angle. And here you can see, yeah, I need to adjust it manually. So edit plot into axis. For the y-axis, I need to change the limit. So I put from minus 180 degree to 180 degree. And you can see that for this frequency or impedance, angle is changing. So you are going from capacitive to from inductive to capacitive, and also you can change. And these are important factors you need to think about them when you are designing your facility or you want to be connected to the grid. Also here you can see that the values are not in hertz, they are in harmonic order. So this 200 shows the 200s harmonic order. It is not representative enough, so let's change them to hertz. In order to do so, you need to go to this edit plot tab, then axis. For the x-axis, and we want to show the frequency, and the frequency in hertz, not the harmonic order, and the range should be from 1 to 10,000, 10 kilohertz. Yeah, you can see that it's not adjusted automatically, so you need to rerun the calculation again. And now you can see that for each frequency, what is the behavior of the impedance there. So basically, this was the presentation. And luckily, we have 8 more minutes for Q&A. So if there is any question, I would be happy to answer it. Thank you so much for your time.
Thank you, Roozbeh. That was amazing. So yeah, we have a couple of questions. I'll just read them out to you, and you can just answer. So the first question is, what can people who don't have access to like expensive software like this do? Like suppose few people may have ETAP or EMTP, but not this software. So is there any student version of it which people can use, or any trial versions they can use?
Yeah, very good question. So this software is an enterprise software, so you need to pay for it. Actually, at the moment, I have access to this software from the university, so the university have paid for it. But I know that they can provide for students some temporary licenses. So if you contact the company, they will ask for some evidence that you are a student, and they can provide you with software. I guess it's not the full version, so there are some limitations. For example, the number of buses or number of analysis that you can do, but you can ask for a better version based on the study that you have. But you need to convince them that you need it and you are a student.
Okay, okay, that sounds good. Second question is there possibility of calculating TDD, total demand distortion, in DIgSILENT PowerFactory?
Actually, I haven't done that before, and I guess you cannot do it by default, but you can. There are some methods using coding and also modeling in PowerFactory that you can build it by your own. So yes, it is possible, but it's not by default there.
Okay, okay, sounds good. And the next question is, are you currently working on any voltage stability problems, like when microgrid with wind turbine is connected to the main grid, something like that?
Yeah, it's a good question. Personally, no. I'm more focused on the voltage dips and the propagation through the grid and different futuristic scenarios. But it can be done with PowerFactory. So voltage stability is actually a kind of thing that you can do there. There are also some pre-developed tools to track those voltage stability, and it is possible to do it with PowerFactory, but this is not my research focus at the moment.
Okay, okay, sounds good. That's all we have for questions. I don't think anyone has any questions as of now. So yep, I think we can end the session. It was very informative and uh, very new things to learn. So thank you for that. It was a really good experience.
Thank you,
And,
Aditha,
mhm,
and thank you all for your time.
that's good. All right, then thank you all. There are no questions, so thank you again for coming, and we appreciate from the entire committee. Have a good day or whatever time you have. All right, thank you.
Thank you. Bye.
Bye. Also, we have a breakout session, networking session for all those who have registered. So just it will start in like 5 minutes. So just feel free to join it. And yeah, that's it. Thank you.